So it's not necessarily an age thing, but people who have reached kind of the ceiling in what they can do with the time that they've got. So they've kind of come to a plateau. Well, we talked before about hypoxia being a kind of a unique stimulus that presses these like adaptation buttons in the body that nothing else can. Well, that's where you can again remove that plateau. You can move it up to the next level with hypoxia. So if we're looking at something where everything else has kind of been done with all the supplements, different types of training, might be time limited to a certain number of hours per week. Well, here's an opportunity for something that actually will make a real difference if you do it correctly.
Okay.
So actually, the cost of that, when you spread it, particularly over a number of years, say, it actually becomes relatively cost effective when we think about actually the impact that could have on your performance.
Barney, with your expertise in hypoxic training, I want to explore a simple question with you today, and that's, can training in a low oxygen environment actually make an athlete faster? But before we get into the science of hypoxic training and all the practical applications, let's start with how you got into researching and specializing in hypoxic training.
Well, firstly, thanks for inviting me onto your show. It's great to be here. I guess my journey as a kind of sports scientist started probably about 1990 or something like that. When I was a young athlete training my sport and wanting to understand more about the training I was doing, how effective it was, and just trying to unpick that kind of puzzle of all this work we were doing. And so that led me to kind of study sports sciences and go on to work towards a PhD. I also started working in elite sport with a sport called sprint kayaking, sprint canoeing, which is a small sport in the UK, but internationally quite big. And so through that process, I was supporting our kind of Olympic athletes as we grew and progressed in this country towards a bit more excellence. And obviously, when you're looking from an athlete optimization perspective, altitude comes up pretty quickly on the agenda. And so kind of towards, I guess at this back end of the 90s, that's why I first got kind of exposure to the concept of altitude training in more detail in terms of practically investigating, exploring it, seeing whether that was something that we could practically apply. And then really from there, as I transitioned out of that team, worked in Canada for a while, got into other endurance sports, cycling and running. It was always a kind of recurring theme. And then probably about 5 or 6 years ago, specifically started in my kind of now academic role. I started to transition into academia, and I'm partly also in academia at the moment as a half-time senior research fellow at Leeds Beckett University. So I started looking at different types of altitude training, particularly intermittent hypoxic training using chambers effectively. Because I'm very interesting new research and outcomes in that area. So they started to gather momentum around that, and then obviously looking at some of the mechanistic aspects, and it just kind of snowballed from there, really. So as a rather long-winded approach, started a while ago, started in elite performance, and has transitioned into kind of more research and application back to sport, if you like.
Awesome. Let's start with the basics, right? What exactly is hypoxic training, and what are the different modalities of hypoxic training?
Yeah, so very generally, hypoxic training or hypoxia refers to a lowered availability of oxygen, if you like, or lowered oxygen in the body. It results from having less oxygen availability in the air, and there's a few different ways of that occurring. But effectively, what that means is in the body, we have less oxygen to use for creation of energy. So we'll get into more detail around what that means. But actually, that's kind of muscle function. And we use oxygen in our body to create energy for sustained exercise output. So the kind of the different modalities, people will be your listeners will be aware of some of these, but there's kind of what we call natural altitude training, so hypobaric hypoxia, so that's kind of technical term, where that's related to a lowered atmospheric pressure. So when we go into altitude and we live at altitude, and and we train at altitude. That's what we refer to as live high, train high.
Okay.
In the late 90s, there was a new concept where we would called live high, train low, where you might live at an altitude for most of the time, but then you would travel down the mountain, if you like, because it's very geographically determined. You travel down the mountain to a lower altitude where there's more availability of oxygen, and you can maintain a higher training intensity, and you train in that area, and that would be your train low. So live high, train low. And that's also kind of morphed into another kind of modality where you live high and you train high and low. So you might live high, you only training at high altitude, and then you will also do some of your training sessions, maybe the ones that are more required of high intensity intervals at a lower altitude as well. And that's what we generally call kind of our natural terrestrial altitude training. And then more recently, I guess the last kind of 15 years, we've had altitude chambers, so simulated altitude. So this is what we call normobaric, so a normal atmospheric pressure, but we're creating hypoxia. And in that environment where we have generally largest chambers where you can actually physically get into them, you might have a bike, a treadmill, other modes. We also create sleeping environments as well. There are some hotels that have hypoxic rooms where you can sleep in overnight. There's tents we can use with altitude generators, and altitude generators where you use a mask system as well, which are pretty practical and available for everyone. And in those, using those modalities, we can either be for durations at rest, so equivalent to kind of living high, so sleeping overnight at rest, or we can do exercise. So we're training high. So we can do interval training, long steady state runs, or sessions, and all the rest of it, and everything in between. So you're kind of simulating what you would do if you went to that altitude, if you like. So those are the kind of different modalities.
Okay, got it. Is there a different adaptation between training or living in reduced atmospheric pressure versus a lower oxygen availability if we split this into separate? So just to create a bit more clarity, because I mentioned it, so when we go to terrestrial altitude, there's less oxygen available to us because of the lowered atmospheric pressure, whereas in these kind of simulated chambers, there's less oxygen available because we remove some of the oxygen concentration. So without trying to get too technical, it's how we get oxygen into our blood through our lung, our pulmonary membrane, alveolar membrane, is through a process of diffusion. So you go from a concentration gradient of a higher to a lower. And that concentration gradient is dependent on what we call the partial pressure of oxygen. And that's determined by the pressure and the concentration of oxygen. Okay. When we go to a higher altitude, the concentration doesn't change. It's still 20.93% of oxygen in the air, but the barometric pressure lowers. Okay, so you get certain part pressure. And when we go into an altitude chamber, the pressure is higher because we're at lower altitude, but the concentration, we reduce the oxygen to reduce the concentration. So the overall partial pressure is equivalent to what happens at higher altitude, if you like. So the same. But obviously there is a difference between a pressure difference and a concentration difference. In terms of how that partial pressure, that availability is generated. And in reality, for what we're interested in terms of sports performance and the adaptations, there isn't really any difference at all. We get the same outcomes. So there are some very subtle differences around the pressure differences of the lung, which may affect diffusion. But for our intents and purposes in sports performance, that's not really important for us. When we go to very high altitudes, that becomes a bit more of an issue potentially. But even that's an area which is limited knowledge, if you like, about the true differences. Okay. When you say altitude and very high altitudes, what are you talking about in terms of meters or feet of elevation?
So we have generally three kind of terminologies for altitudes. We have moderate altitude, where we're really talking about kind of 1,500 meters to kind of 2,500, 3,000 meters. And then about 3,000 meters to kind of 6,000 meters would be high altitude. So we're getting into kind of mountaineering terrain then, high mountains, alpine regions. And then we have and Himalayan, lower Himalayas, let's say. And then we have extreme altitude, which would be more like 6,000 meters upwards, which is kind of more, you kind of, 8,000 meters type terrain, high Himalayan mountains, and things like that. So when we're talking about altitude for sports performance, it's really in that kind of moderate altitude band that we're talking.
Okay, the 1,500 to 2,500 kind of.
Yeah, 3,000 maximum kind of thing. Yeah.
Okay, so that's kind of that in that range is not enough to actually develop any kind of altitude sickness, right? It's not high enough.
Yeah, I mean it can do at the top end.
Okay.
There are reported cases, if you went suddenly from being at sea level and you went up to 3,000 meters straight away and were quite active for a few hours, you might start to develop a little bit of a headache. But not many people, to be honest. It's unusual that would happen. But there are some cases where you can get house sickness in extreme cases. But it's usually when you're higher than 3,000 meters for sure.
Okay. So let's talk a bit about what happens mechanistically inside the body when someone has gone into altitude or when someone has done deliberate training in an altitude 10, so to speak, right? So what's happening inside the body that improves, would it be the oxygen delivery to the muscles or, what's the chain reaction in there? If you're using your sports watch or a generic formula to calculate your zone 2, there's a very good chance that you're not training in your true zone 2. And that's not because they are intentionally doing anything wrong. They simply don't know your individual physiology, so they estimate your training zones using population-based formulas. The problem is that if your zone 2 is estimated incorrectly, you can spend months or even years training in the wrong zone without ever realizing it. And that's a much bigger deal than most runners think. Zone 2 isn't an arbitrary heart rate. It's your own individual physiological tipping point where your body reaches its highest rate of fat oxidation before it starts relying heavily on carbohydrates. That point is different for every runner, and it also changes as you get fitter. So no generic formula can tell you exactly where it is. Which means if you're training from estimated zones derived from formulas, there's a good chance you're not training the energy system you think you are. Below your true zone 2, your body adapts to become better at burning fat, building the aerobic base that supports everything from endurance to speed. Drift just above it, and now you're training your body to rely more heavily on carbohydrates instead. That's not a bad thing, but it's a completely different adaptation and not the one you're aiming for. For years, I've used heart rate to measure training intensity, but heart rate is influenced by things like heat, hydration, caffeine, sleep, and fatigue, just to name a few. Then I thought lactate was the gold standard until I realized that lactate also changes depending on glycogen availability and your nutritional state, making it just as inconsistent as heart rate. That got me thinking that your breathing is one of the closest reflections of what's actually happening metabolically, because it's driven by your body's physiological response and not easily influenced by those external factors. As exercise intensity increases, your muscles gradually shift from burning more fat to burning more carbohydrates, which produces more carbon dioxide that your body has to remove by increasing your breathing. That change in ventilation happens at your own individual physiological thresholds and not at a generic percentage of your maximum heart rate. That's why learning about the VitaPro from Timeware was such a breakthrough for me. Instead of estimating training zones from generic formulas or indirect markers, it measures your breathing in real time to identify your own individual physiological thresholds that are not influenced by external factors. If you're serious about building your aerobic base, improving endurance, and making sure that every zone to run is actually doing what it's supposed to do, I think it's well worth looking into. Timeware is giving listeners of the Endurance Lab podcast $100 off their pro training membership when you use my link in the description with my code ELABTW26. And if you'd like to understand the science behind it all, check out my full conversation with Timeware founder Anar Larosan, also linked in the description below. So what's happening inside the body that improves, would it be the oxygen delivery to the muscles or,
Yeah.
What's the chain reaction in there?
Yeah, so I think there's we're trying to kind of keep this relatively simple. There's first of all, there's an acute response. There's an initial response to altitude.
Okay.
So you're at sea level, and then you take a cable car, you drive up to altitude, or you go into a chamber and do some exercise. There's that initial kind of response to the body senses. So what I have to think about is, and then there's a chronic one, which I'll get to, which is something that's built up over time, how your body long-term responds and changes to those repeated exposures to altitude, let's say. So first of all, we have to understand that how important oxygen is to us. We talk about energy, basically, to provide energy that supplies our muscles to create muscle contractions that allows us to run at a certain speed, cycle at a certain intensity. So that oxygen, it enters the body, as we've described, through the lungs. So you breathe in, it diffuses from the lungs into the blood. That oxygen is picked up by red blood cells, hemoglobin. It binds to hemoglobin. It travels to the area of need. Now, all tissues in our body need oxygen because we use oxygen to create energy. But when we exercise, it's predominantly channeled towards the muscles, the muscle fibers that are being used. The brain needs quite a lot, so organs need a lot. It goes to those muscles. Obviously, the heart needs quite a lot of oxygen because that's pumping away. Yeah, your muscles need that as well. But there is a general shutdown over time of limiting blood to non-essential organs for that activity. So it starts to channel those muscles. So we get a greater diversion of that blood flow to those muscles. The blood goes into that kind of network, a vascular network, capillary network within the muscle, and then it diffuses from that capillary bed across the membrane into the muscle fiber itself, where the oxygen will then make its way to the mitochondria, where it's used, and in the cell itself, you've got glucose is broken down, fatty acid oxidation as well, and then we create ATP, which is used to contract the muscles, and that's the cascade. Okay, so that's only what's happening. But when we go to altitude, there's less oxygen in the air, less oxygen diffuses across the lungs into the blood. We see less oxygen in the blood itself. So when we measure, people are probably familiar with these little monitors, SpO₂ monitors.
Yeah,
they go on your finger. And they give a reading. When at rest, it's like 98, 99. You see people in hospital, and it might drop, to like 92 or 3 at rest, and then the doctors get a bit worried because there's some sort of compromisation, some sort of compromise somewhere along the line. Now in altitude, if you did that, even at rest, depending on the altitude, that concentration will drop, and that's reflecting the kind of the concentration of oxygen in your arterial blood. So the blood is going to the tissues. So, and sorry, just to ask, is that a percentage or is that the absolute amount of oxygen? It's reflected as a kind of percentage of rest. What's normal, if you like? What's a normal? Yeah. So it's very comparable, if you like, between you and I. What sort of what 95% is, if you like. It's the saturation. If you like. So then we have less in the blood. And that means when we're exercising, if we're using the same rate of use of oxygen, which is our kind of VO2, if you like, not VO2, VO2, our rate of use of oxygen consumption, then what tends to happen is that concentration of oxygen in the blood reduces and gets lower and lower because we're using it at a greater rate that we're supplying it. So the body's initial response is, right, well, actually, there's so many feedback systems. Well, first of all, wow, I need to pump up my heart harder. I need to get more oxygen being delivered, and then I have to ventilate more to get more oxygen into the lungs. And those are the two initial things that happen, essentially. So very quickly, you'll notice a higher heart rate and a higher ventilation rate. And really, acutely, that's all the body can do. You can't do much more than that. There's a bit of vasodilation, a bit more opening of the blood vessels in the muscles that require the oxygen. But again, you're kind of limited. So very quickly, your exercise intensity starts to drop because all of a sudden you can't maintain that intensity because you can't supply enough energy. Yes, you can produce some anaerobic energy, but again, that's only only limited for a short period, and lactate starts to rise and acidity starts to rise, then we start to get fatigue. So that's an acute response. Now, every time we have that acute response, there's a certain triggering of mechanisms that create a long-term adaptation, which is really what we're interested in.
Okay.
And I won't go too much into these signaling pathways necessarily, but effectively, what happens over time is the body senses that there's less oxygen in the blood. It's the muscle cells themselves sense that there's less oxygen, and it kind of triggers different responses. There's a peripheral response that happens in muscles that are being used, or the muscle cells that are being used. So it's not a global response. So it's peripheral responses. And then there's what we call a central response, which is more of a blood-based response. And we need to think of these two things quite separately, because we can influence each one slightly separately. Okay. So and we'll kind of come back to this.
Okay.
But if you continue to give kind of these, what we call desaturations, if you like, within the blood or in the muscle, then it triggers these adaptations. So the more exposures you give, more desaturations, the more of these adaptations occur. So when we talk about altitude training, we need volumes of time. It's not just, we don't get much effect from one exposure, if you like, on one altitude session. It's repeated and repeated, just like any other training effect, right?
Yeah, consistency.
Yeah, consistency. So just to go into these adaptations, the critical ones. So if we think about central ones, which is probably what most people are more familiar with.
Yeah.
So the kidneys play a role here, because the kidneys sense this lowered oxygen concentration. And so in order to combat that, they say, well, I need to produce more red blood cells. So it produces a substance called EPO, erythropoietin, most people are familiar with, for mostly the wrong reason.
For doping. Yeah.
But that gets produced in the kidney. It travels to the bone marrow, where there's a process of generation of increased red blood cells. So again, that's not like an instant tap. It needs to be persistent over time. So there's a whole EPO response, and then the bone marrows will start to produce red blood cells in response to that. But once the EPO response goes away, then that starts to shut down, and so no more red blood cells are produced. And the red blood cells, they start off as very small, immature cells, and they start to develop into bigger ones. And as they get to bigger ones, they can hold more hemoglobin, they can carry more oxygen. And so as we do have these repeated exposures, or this kind of chronic long-term exposure, to even low levels of altitude, or we get in response an increase in hemoglobin mass. And that's what we're after.
Okay.
One of the things we're after. It's not the only one, it's not always the most important one, but it's one of the key adaptations that we get. So what that means is that the blood can now extract, hold more oxygen to start with, so it's kind of reservoir of oxygen in the body is bigger. But it also means that when we breathe in, even if there's less of this kind of partial pressure, less available oxygen at the lung membrane, we've got more hemoglobin for it to diffuse and lock the oxygen to diffuse and lock onto. If there isn't much hemoglobin, then no matter how much we breathe in and out, you can't add any more oxygen to that pool, if you like. So this increase in hemoglobin mass becomes really important, because then we think about that kind of pathway of oxygen from the lung to the muscle, what we call the oxygen cascade. Then it enables us to actually deliver more oxygen to the muscle itself. Okay. So that's this kind of main central adaptation that we get. Okay. The next one, the other one, is the peripheral adaptation, which, to be honest, hasn't really traditionally been given much attention. It's only more recently that this has been understood as a key mechanism, a key response to altitude training. So, most of your listeners will be familiar with altitude training equals increased hemoglobin mass, if you do it correctly. But they won't necessarily be familiar with the peripheral adaptations, so adaptations within the muscle. So most people are familiar, and I'll, again, trying to keep this fairly light, but it is important to understand. Most people are familiar with the fact that any cell has a nucleus, has DNA within it, and a muscle cell or a muscle fiber is no different. Okay.
Okay.
Now, when that muscle fiber is short of oxygen, so it has a lowered concentration of oxygen, because we're using it at a faster rate than we can supply it, then it gets this kind of signal, if you like. Well, first of all, we get an increase in something called reactive oxygen species. Body could be short of oxygen, but actually, what that does is it triggers these hypoxic inducible factors, and we have two main ones of those, HIF1 and HIF2. And then what they do is they actually trigger when they are kind of stabilized, put into effect because of localized hypoxia within the muscle fiber, and that stimulates a whole load of adaptations which are very beneficial to us for exercise performance, and no matter what altitude, sea level altitude. So it improves our mitochondrial function. It improves our ability to transport lactate out of our cells, out of our muscle cells, and most importantly, probably, it actually increases the capillarization. So what those, and there are some other factors that go on as well, but these kind of key primary ones mean that actually what it's allowing us to do is within the muscle itself, get more oxygen to the muscle fibers at a higher rate, use it more effectively, and just improve the function of the muscle cell to continue to work kind of aerobically, if you like. So you've got two things that are going on, and actually, depending on your individual makeup, depending on your sport and events, it will very much depend on which is most important to you. It might be hemoglobin mass, it might be peripheral that's important to you, or it might be a combination of both. How we use altitude will determine which of those we trigger and when, basically. So I hope that kind of makes sense. It's basically central and peripheral, and they act.
Two kinds of adaptations to be had.
Key areas of adaptation. The other key thing to understand is that the central one can kind of be triggered. Hemoglobin mass can be triggered by a few different, like it's not sport specific, if you like. So that can be done at rest. It can be done during exercise. Whereas peripheral adaptations are very specific to the muscle fibers that are being used. So that means, if you're a runner, you need to ideally run. That'd be most specific. But cycling wouldn't be too far off, for example. And if your event is a very, is ultra marathon type stuff, then you need to be specific about recruiting those muscle fibers that you use in that event. Whereas if you're like an 800-meter runner, you need to be very specific over more high intensity exercise, because you need those muscle fibers to be recruited, if that makes sense. So, and that kind of reflects when we get onto it, if we get onto that far, slightly different types of interval training that we do in altitude, because they tap into these different kind of muscle fibers.
So on the muscle side of the adaptation, is it safe to say that in order to get those adaptations in the muscles, the training should be done in altitude? So it would be trained high?
Yeah, basically. You have to get those adaptations, you need to be training. You need to do training in altitude. You don't get no rest in altitude.
So central adaptations can come from training low and living high, so to speak.
Yes.
Okay.
Yeah. So to get those central ones, and this is typical, and there's lots of examples of it. You'd either go and live at altitude for a period of time. You would use a tent to sleep in, or what is becoming quite popular and common is for athletes to convert their bedrooms, the living areas at home, into creating a simulated altitude, so a normal baric hypoxia kind of environment, so that they can actually live and sleep at altitude as well. So you don't have to have, so it's much more convenient as well. So
with the approval of the wife.
Yeah, and that's the challenge. Other people know what we do. But there's some good health related benefits of hypoxia as well. So, there's always side benefits too. Whereas if you want the peripheral adaptations, you have to exercise in altitude. Now that could be, again, going to real altitude, or it could be in a chamber, or it could be with one of these mask systems to create those.
Okay.
So a few different options for sure.
Okay. We'll definitely get into the equipment that we can use a bit later. But first, so, I think most people live at sea level or very close to it. And if we ignore races at altitude and focus purely on sea level performance, right? I know we talked about the adaptations just a second ago, but what does the evidence actually say about relating those adaptations to actual performance in the real world? So if I train with less oxygen availability and less atmospheric pressure, but race at normal levels, will I actually have an advantage on race day?
Yeah, that's the number one. That's the critical question, right? So let me just. I'll come straight back to that, but just to say, probably it's worth people understanding that if you race at altitude, then it has an impact on your performance. So without a doubt, you need some sort of adaptation for altitude. You need to do altitude training if you're going to maintain or mitigate some of those reductions in performance. Okay, so that's without question. Like, you have to do that unless you're a sprinter or very short duration, or England, football. Any of the football teams playing at the Azteca Stadium as we had the World Cup. There are certain situations where you can travel to altitude, stay there for literally a couple of days, perform, and yes, it will impact you, but it might not have as much of an impact as you think, depending on your sport. But basically, endurance sport, we're so dependent on oxygen, and it's not a technical sport particularly. So we need the altitude adaptation. But if we think of what happens at sea level and sea level performance, that's where the picture actually isn't quite so clear.
Okay.
And if we look purely at research, and research, what we have to understand, doesn't always reflect real world either.
Of course.
Research isn't always done on elite athletes or highly trained athletes. It's done on mixed. Research will have an intervention, so it might be that people will go to altitude for a certain period of time. Everyone does the same thing, and then there might be a set period before there's a performance trial. Okay? And that performance trial, any kind of performance, whatever distance, what kind of event it is, it's not just about the energy you provide. It's about other things as well. Being prepared and ready and recovered and having a good race strategy and being well practiced at that and all the rest of it. So, and there's individual variation. If you measure yourself doing a 1500 meter race, let's say, or 10K, one day to the next, your time isn't going to be the same day after day after day. There'll be variations depending on how you felt on the day, how recovered you were, what weather was like, your mechanics on the day, what's happening around you, all these kind of things. So what's clear though? So there's a few different things. What's clear is the physiological determinants of endurance sports. We understand what that is, and we know that in the right circumstances, with the right type of altitude training, which is also quite varied, and that's the caveat to it. If it's individualized, we can have a huge impact on the physiology. And now it's really then up to, can we translate that into the performance? So if that performance is heavily dependent upon large amounts of oxygen coming into the body, and there's fewer other challenges around, whether it's like pacing or tactics, or other technical skills or anything like that, then really that person should be able to translate that to performance.
Yeah,
but it's not. Okay. And that's part of the training process, isn't it? It's like we do that other thing. We do a certain amount of one type of training, then that's a component of our race. But it's up to us to try and put that improved capability into effect. Right?
Yeah.
So there is an element where, just to carry on that same theme. Actually.
Sure.
Because research kind of gives us one side of the picture, but then there's also reality and real life, and there's probably the majority of altitude use isn't around research. It's actually just practical application by athletes themselves. And there's much greater knowledge now around individualization and how, I've just talked about some of the mechanisms and how they apply.
Yeah.
even like 10, 15 years ago, we didn't have that level of understanding because the science wasn't done because our technologies weren't more developed now to develop this understanding. But we have a much better way of individualizing altitude training now, different types of it, when we do it, how we do it, monitoring the load and the dose, and these kind of things, and understanding about events. So from an athlete perspective, there's many examples now where in endurance sport, at the very high end, nearly every kind of high level performance is underpinned by some level of altitude training. It's in there somewhere to some extent. It might not be immediately before that performance. It might be somewhere in the background. It might be living at altitude, or it might be using a tent at home, or intermittent sessions, or something around there, because of the importance of the physiology in that performance that we know can be manipulated around hypoxia. Hypoxia is such a strong stimulus that sets these adaptations that I've described. That it's very difficult to get those adaptations to the same extent using any other modality. So that's why it's so attractive, because it's a kind of for the body. It's like if you haven't done it before, it's like a novel stimulus, and it makes these specific changes that we can't really get through any other means. We get some of them to a little extent, but it's a really powerful signal. So even, for example, Josh Kerr's recent mile record, he's described himself how he's had an altitude. One of the big factors for him recently was not the only factor, but a big change for him has been getting his living quarters, with bedroom at least, converted to an altitude environment, so we can get some of those central adaptations, for example,
or the canyon runners for the matter.
Exactly. So there's so many examples when we look to elite athletes, whether it's runners, whether it's cyclists as well. Within professional cycling teams, altitude is still a huge key component, bigger now than it used to be, as well as people are seeking these every single competitive advantage they can get. They're trying to optimize the body at every level, and altitude plays a role in that. So when we look to research, because of the limitations of research and the groups and all the rest of it, and the inability to individualize when we're doing randomized controlled trial type approaches, it's a mixed outcome. Some studies will say, clear improvement in performance, others not. But where we do have that, the correct type of altitude intervention for that person, for that event, and then it's blended nicely into the actual when the performance takes place for that individual, then mostly, if we can unpick it from all the other types of training, we see a performance improvement. So it's not an easy one, but I think for anyone involved in high level endurance sport, it's fairly clear that it's going to be of benefit. The question is whether that individual and that team can
translate it over to the performance.
And has enough knowledge and control of the conditions to be able to get the effects that they want.
Okay. So the adaptations are real.
Yep.
The physiological changes are real. The only question is whether we can translate it on race day with the correct fueling, the correct strategy, the correct pacing, the correct whatever that happens on race day that is not, that you can't plan for. If that aligns, then those adaptations will allow you to show that improvement. Is that safe to say?
It is. I mean, there's a few, absolutely. I mean, the challenges as well are that, when you go to altitude, intensity will drop. Your general training intensity drops. So that becomes a little bit of a challenge as well. So if your event requires high intensity work, then you've got to find a way of still maintaining that, still keeping it at a high level. Otherwise, effectively, if you go to terrestrial altitude, you might be there 3 or 4 weeks. You've had 3 or 4 weeks of really good, endurance stimulus, but actually it's all been at a slightly lower pace. Right?
Yeah, your specificity is not there, right? Because your power output would be reduced in altitude or in a tent. So you're not exactly getting that training specificity that you normally would if you were at sea level.
Yeah.
Is that correct? Yeah.
Okay. So,
okay.
When we train, as I said before, there's there's lots of different kind of signaling pathways that give us a whole range of adaptations. And altitude hits a number of those, and it's often those that are not really challenged normally at sea level training, but it's quite difficult to still stimulate the others. Now, you can do that with careful planning and good knowledge.
Okay.
But it's easy for people, if they don't have that, to not keep stimulating those parts of the adaptation kind of pathway spectrum that are important for that performance. So, for example, if you're a 5K runner or a 10K runner and you do a big altitude block and if you haven't spent much time at true race pace, then when you come out from altitude and you go to race at race pace, there's obviously a mechanical limitation, but there might be other aspects, like your anaerobic capabilities might not be as good as they were before. So you've still got to make sure that you pay attention to the other things as well. And this is actually where the mode of altitude training becomes quite important. So, do you live high, train low, or live high, train high and low? So you're doing some training altitude to get those peripheral adaptations that we were after and the central, but then we travel low to make sure we can still maintain intensity and do some intensity work. And that's a really, really attractive modality. But then
there's a very hybrid approach to it.
Yes. Yeah. But it becomes quite logistically challenging because there's actually not many places in the world
that allows you to go up and down.
And then there's a travel time up and down. Even if it's just an hour trip, or a cable car up and down. It becomes logistically challenging, and that's actually where some of the normobaric hypoxic modality, like chambers or the mask basis, become really useful because actually you can do a 10-base system at home, so you can get the central adaptations. You can do the intermittent hypoxic work, so you can be on an indoor trainer, treadmill, and you can do your specific exercise-based hypoxia sessions, and you might only need to do 2 or 3 of those a week, and the rest of your training is all normal, so you can do everything you need to do. And actually, if you do enough of the exercise-based hypoxia, you still get the central adaptations at the same time. You don't have to do the sleeping intense piece.
Oh, okay.
So, and we found that with our work quite successfully. That's a really good kind of approach. So a lot of your training, your lifestyle is just adding in 2 or 3 sessions a week of this hypoxic training in your own home, in a gym, wherever your local altitude center is. So that's easier to integrate. Yeah,
that makes so much more sense for a master's athlete that is not a pro athlete that has the ability to just leave everything and go spend 6 weeks in an altitude camp. We've got families, we've got kids, we've got jobs, we've got responsibilities. We can't just disappear for that. But on that point, on altitude tents and chambers, is the efficacy of that the same as actually going to altitude?
Very much so. I mean, that's quite a good bit of research. I mean, at the end of the day, it all comes down to, like anything, it's like the dose that you're getting, right? So we talk about training loads, don't we? And the volume you've done, the distance you've done, the time, the speed you've run at, and it's the same with altitude. Although we look at the dose not so much in terms of how far we've run or the exercise intensity that we've done. It's actually how low is this the localized hypoxia within the body. So we measure that with SpO₂, and how much of that reaccumulated in the time. So what we do with our athletes is we will measure and monitor SpO₂ at the finger or the ear. We'll also have a monitor on the leg, so the near infrared spectrometers, devices that we use to look at muscle levels of oxygenation, and we're looking at both the central from the finger or the ear and the local, the muscular peripheral desaturation we're getting, and we're progressively loading that person. So whether that happens at altitude or whether it happens in simulated altitude, if you like, can be exactly the same.
Okay.
So it's more about getting those things right. So, an hour training in an environmental chamber at 2,500 meters would be the same as outdoor training, at 2,500 meters. You're getting the same stimulus, if you like. But the nice thing about doing it in a chamber or with a mask-based system is actually, because people very quickly acclimatize. So we might start at 2,000 meters. We might, over a progression of weeks, go up to 3,000 meters. So you might go 2,200, 2,400, 600, 800, 3,000 meters as the body adapts. So we're progressing and maintaining the level of kind of stimulus to get more adaptation. If you go to one altitude and stay there, then it's very difficult to then say, well, actually, I need a bit more altitude now, because I'm adapted. I need more stimulus. So the kind of the adaptation response is very big to start with, and that's where it's very easy for athletes to overtrain at altitude and altitude camps to actually getting less and less because you've become adapted to it. So using a normobaric hypoxia, so a chamber or mass-based system, allows you to have that control and really determine what dose you're having. I mean, we find with our athletes as well that because the exercise intensity is slightly lower, because you're at altitude, it's actually easy to add it in as an additional session. It's like a lighter session, or you might do, half an hour or 45 minutes normal session, and then you add on 30 minutes at the end of it, sort of thing. We have split sessions and things like that. So it's half hypoxic, half normoxic.
Or your more recovery, like low zone 1, zone 2 kind of sessions, you can do it in those chambers.
Yeah, exactly. So you can accumulate time. We still want to have intensity specificity where we can. So we still want to try and recruit those same kind of muscle fibers. So if you're a 10K runner or a half marathon runner or a marathon, we still want some time spent close to race pace, but it wouldn't have to be as much, obviously, because it's in hypoxia. So
Okay. Can we take a tangent with a slightly different question? Is there a misconception about hypoxic training that you see athletes having?
I think so. I mean, I think people, first of all, think people see that the main one is that hypoxic training is just one type of training. You just go to altitude and that's it. Well, actually, as we've described, there's lots of nuances to it. There's lots of different ways you can do altitude. I'm not sure it's a great analogy, but I kind of liken it a little bit to like going in the weights room. You can go in the weights room, but there's 50 different ways you can use weights to get different outcomes. Right? Yeah. It's just a way of getting a stimulus. So you could do high load, 1-2 reps, or you can do light load, 30, 40, 50
reps.
Short rests, long rests. You can compound exercises. You can whatever you want to do. You get slightly different outcomes depending on what you want. And it's the same with altitude. It's not. It can be very specific how you use it to get slightly different outcomes depending on what you need. And I
guess you have to start with the goal in mind and work backwards. What modality or how are you going to structure that training? With the weights, with altitude as well. If you don't have a goal in mind, you don't know. You're just not going to get anywhere with it, right?
Yeah, exactly. And so, and the other kind of thing with altitude is, and again, the analogy to gym works quite well, is that when you go to the gym, you can be very specific. You have a 45 kilogram weight for this exercise, and you're doing 10 reps, let's say, or something like that, and you're doing this muscle group. When you go to altitude, because it's very difficult to measure the stress on you because of technology. So I've talked about measuring SpO₂ on your finger, but actually the ways we do that, they're quite limited to the technology. We can do that at rest very easily, but actually while we're exercising, it's quite tricky. Not many of these sensors are practical to run with, for example. Not many of them actually record the data continuously because SpO₂ values will change all the time. So when we finish the training session, we know how far we've gone, we know how fast we've gone, we know how long that is, but actually it's not always clear how much hypoxic stress is to us, right? So imagine going to the weight room and saying, right, I'm doing some weights, but I don't know what weights I'm pushing, and I'm not counting reps. It's like your outcomes in terms of what you're trying to achieve would be really poor, and that's a little bit what happens to altitude. So there's this misconception that people say, oh, altitude doesn't work, right? Or I've been to altitude and it hasn't had an impact, so therefore altitude training doesn't work. But actually, it's how well structured was it? how well controlled was the intensity, was the progression, was the exposure, was everything else in place? Did you have good iron stores, so actually you could create red blood cells and more hemoglobin? How well was your intensity control relative to your sport? How long did you go? All these kind of things. There's so many things that affect whether it's successful or not, and someone's perception of success or not as well. So I think there is a misconception over it. People are very binary. It works or doesn't work. Well, loads of areas in between that. And if you do it wrong,
correct,
it might work for you in terms of physiology, but as we said before, if you don't translate that into performance very well, then again, it doesn't work for you really. Because it's not got the performance outcome. And that's what we need to be really careful of. And it's only successful with any training intervention if we can actually translate.
I was just going to say that.
Into the performance. So, So there's that misconception. So I think those are the main things really. It's either it doesn't work, or it doesn't work. I think it's the conception.
Well, I guess it's also the same for just basic training, right? If you just go out and run or cycle without a specific plan or without a goal, and then you go do a specific event, you will never have the best adaptations for the time you put into the training for the goal if you don't have a plan that is tailored for that goal, right?
Yeah.
Or if you use the wrong plan, if you train for a marathon but you want to run a 5K, the adaptations that you're trying to get, you get the general adaptations, but not that specific adaptation for that event.
Exactly.
Can you relate it? Okay.
It's exactly the same principle. It's nothing magical. It's just something that people aren't probably used to. It doesn't work on the same basis of how we understand the normal sea-level training, because it's not about necessarily the load that you do. It's about actually how much, what we call again technical hypoxemia we get. So how low is the oxygen saturation in the blood? How low is the oxygen saturation in the muscle itself as well? It drives adaptations. And that's determined by exercise intensity, the kind of duration, but also what altitude you're at as well. So whether at 1,500 meters, 2,000 meters, 2,500 meters, 3,000 meters, it will vary what combination of those you can kind of achieve, if you like.
On the point of measurement, some watches, I may be wrong, but some watches actually do give you your SpO₂ reading. Are those accurate?
Generally, generally.
Okay.
Yeah,
I thought so.
There's not. I mean, it's just not a very good location. There's not much kind of blood perfusion around that locality. For some people, it all depends very much on, in every individual is slightly different in that wrist area in terms of blood perfusion, where veins and arteries are and all the rest of it. So for some people, it may work well if you've got really good contact. So some people have to really tighten the watch strap to get really close contact. But generally, it's not regarded as being very sensitive or reflective of it. So there are a number of other systems. We use a system called OxyWear, which is a little system that sits on the top of the ear. Another one we often use as well. There's no ideal solution, but that's really nice because it sends the data to an app, and you can monitor that in real time, and you can record it as well. There are some other apps available too, which will take that information or other SpO₂ readings. Fingers are useful. There are some individual wireless devices which will store and transmit Bluetooth data too, but fingers not always that useful. So it's finding a solution that's good, and I'm involved with a group where we're trying to find good solutions and solutions to make this a bit more available, because that's one of the limitations for us moving forwards. Actually, is
to measure
this. A little missing area at the moment. So
I want to move on a little bit to how heat training and hypoxic training can complement each other, as well as some more specific tools or equipments that people can use, tents and all that kind of stuff. But before we do that, you mentioned that without properly tailoring your hypoxic training or your altitude training would not result in the kind of results that you want to get. So do you or your team in the university offer any kind of consultations for someone that is interested in, for a normal training plan, there are tons of coaches online that you can buy a training plan from. You can go to Training Peaks, you can get a plan for, but it's not so accessible to get a altitude or hypoxic training plan online, right? So do you offer the kind of customizations for someone online if they're not in Leeds in the United Kingdom? Do you offer any of those kind of services?
Yeah, absolutely. So through the university, we have a really good setup for consultancy, and we do work with a number of groups at the moment, national level groups and individuals. So through Leeds Beckett University, if you go onto their website, there's the Health and Performance Hub. You'll find if you search for that, you find a website, and you can book consultations. And we do a lot of, well, first of all, we have environmental chambers where we train athletes in. We test athletes as well. So we do the whole approach there in terms of interventions, monitoring, support. We provide
designing plans and all that.
The mass generator systems, so you can take those home as well.
Okay.
So when we do that remotely, we can do remote stuff, and people can come and visit us in Leeds as well. But people can also get hold of me through LinkedIn. I do private consultations as well outside of Leeds. So there's different ways of doing that. So yeah.
Okay, I'll link to that in the show notes. So if someone's interested, they can reach out to you. Yeah. Okay, going on to heat. I understand that you spend also quite a bit of time researching heat acclimation, and I had your colleague Dr. Daniel Snape on the podcast a few weeks ago, or was it a month and a half ago, about heat training, right? So both heat and hypoxia, I understand, are different stresses, but both ultimately have an effect on endurance performance. How are the effects of heat and hypoxic training different physiologically?
Yeah, so I won't. It's great that you had Dan on. He's really knowledgeable in this area, and we work closely together in these areas. Interestingly, in the last few years, it's all quite new and novel. Actually, it's this understanding that actually some of the benefits we get from heat training can have a similar adaptive stimulus on the body to hypoxia.
Okay.
So, and it's still quite emerging. So, we don't have a strong understanding of exactly kind of the exact interventions where they cross over, but mechanistically. So for the background physiology, what we know is, and if you'll remember from the talk from Dan, he talked about some of the adaptations that occur, and one of them is an increase in plasma volume. So if the body is exposed to high core temperatures for a sufficient period of time, and it doesn't have to stay long, but the first thing the body does is increase plasma volume, so you can hold more fluid for sweating and all the rest of it. Now, again, if you remember with hypoxia, we talked about the role of the kidney in those central adaptations, right?
Yeah.
So it senses the low oxygen concentration in the blood because of hypoxia, because less available oxygen. Well, when the plasma volume increases, that actually dilutes the hemoglobin in the blood as well.
Correct, yeah.
Right. So the kidneys, again, sense this lowered concentration of oxygen.
Okay.
In the blood, and it has a similar response. It's right, I need more oxygen. I'm going to create EPO, and that goes to the bone marrow, and then we get an increase in red blood cells. Now, the increase in plasma volume, it never kind of decreases the concentration that much. Like, it does decrease it, but not to a huge amount. But the nice thing is it's continuous. It's always there. Even when you're not, because it's an adaptation. Once you step out of the heat chamber, it's still there, right? It's over time. And so, again, it's a little bit like living at altitude, living high. You get a similar kind of chronic response. So all the time you have this EPO drive that produces red blood cells. So to say it's not as potent, we don't think. The evidence doesn't suggest it's quite as potent. So when we look at like a heat intervention, like a 2 or 3 week heat intervention, then we're not getting quite the same response in hemoglobin mass as you would from a really effective altitude camp. But nonetheless, it's there, right? It's in the background. And that is a route by which some athletes and teams are using, saying, well, rather than go to altitude for this really high level potent response, we're going to do heat training and get it that way. Or we're going to combine it. We're going to do altitude training, and when we come down from altitude, we can do heat training to kind of maintain that hemoglobin mass we've developed at altitude. So it's quite a nice take on it. Now, again, the research is pretty recent on that, still quite new, but it seems that it is a real thing. It does happen. But exactly what the combination of heat training is for every individual, that's not quite clear. But also, generally what we do with heat interventions, we generally do quite short heat interventions, like 10 days often, maximum. And so, but actually to get these hematological changes, we need longer interventions than that, like 3 weeks, 4 weeks. Which isn't out of the question, but at least, but it's still, but it's possible to do those. It's longer than we would traditionally do. So that's one of the changes that happens. So that's a kind of a matching effect. Now the other one is when one of the other adaptations. I'm sure Dan probably talked about it, but one of the other adaptations to heat is the production of heat shock proteins within the muscle, within the tissues, body tissues. So there's a kind of protective effect, and there's a number of different types of heat shock protein that are produced. And again, these are basically proteins that the cells, which are produced in response to the heat, that reside within the cells, and they have all sorts of different effects. But one of them, again, is just similar to we had at altitude, seems to be that it stimulates these hypoxical inducible factors, HIF factors that we talked about earlier. And again, that has similar kind of effects where you're getting this increase in capillarization, for example. So some of these same effects, again, we don't think it's quite to the same level, but we think it does happen. And so again, there's this idea that we might get some of the adaptations through chronic heat adaptation, heat exposure, but probably not to the same extent that we get from good hypoxia interventions as well. So it's a really interesting area, and we have to be a little bit cautious about recommending it because it's still quite new, still quite novel. There's not as much known about it, but and I think in some cases it becomes like an absolute kind of no-brainer. So, and a really nice benefit. So, for example, if you're a sea-level athlete and your events that you're targeting happen to be likely to be hot, right? Again, as you learned from Dan's talk, well, you need to become heat adapted. Otherwise, one, you put yourself at a health risk, a serious health risk. But two, you can mitigate some of those effects of the heat, similarly to altitude, by getting those specific heat adaptations, so you can maintain a higher performance, running speed, pace, whatever. So, so if you have to do that anyway, then you might say, well, if I prolong it a bit more, then I can get some of these other adaptations similar to you would get from hypoxia. Now, probably not to the same extent, but in that circumstance, it's like, well, yeah, great, I can do that, and I might be getting a double benefit and an overall performance, not just the heat. I might be getting these secondary benefits. So that's a really sensible approach. And I'm sure Dan talked about different modes of heat training and what.
We did. Passive, active, exactly. And all those modalities. And so I guess if heat was a lever and hypoxic training was a lever, the one with a bigger bang for the buck would be to pull the hypoxic lever training. If you're racing in a condition that is not super hot. But if your race is going to be really hot, having the heat training would be a very good complement to the hypoxic training, and it can be a synergistic effect as well because of that crossover. Is that correct to say?
Exactly. So and that's where the kind of the choice becomes. So just as you exactly described, but if your event is in the heat, then it's probably first and foremost you need to do heat training to get that protection for yourself. That'll be most beneficial. And then ideally on top of that, and this is what a lot of athletes will do as well, they'll also add in some hypoxic training too, mindful of the fact that you've got these two quite strong stressors going on. But if your event isn't in the heat, then it's like, okay, well, actually I'll mainly target hypoxia, do it that way, get a very strong stimulus for adaptation that way.
Okay.
So obviously winter sports, those kind of things are no brainer that way. But just looking at your event and where it is, then you can choose. But it's interesting. The whole landscape of particularly ultra endurance events. There's quite a lot where they're also occurring kind of moderate altitudes too. Mountainous terrain, where even short periods at altitude you would be encountered, and even for those, there'd be a big performance benefit from becoming altitude acclimatized. And some of those are also in the heat too, as well. And so it's actually making sure you're adapted to both. And the interesting thing with heat is that you can get quite hot easily, without necessarily realizing. It doesn't have to be a hot environmental temperature. When you combine with the heat you're producing, maybe where there's less cooling from the breeze or the air, you might be surrounded by terrain that's absorbed a lot of heat. You're just getting this cauldron of heat.
Yeah,
but very quickly that turn badly. So there's a good reason for doing heat too. So
okay, let's talk very quickly about the equipment someone can use for hypoxic training, right? So most of the listeners of this podcast are recreational masters athletes the chance of them going to an altitude camp is almost zero. So they are probably going to resort to equipments that they can use in their homes without altering their lifestyles too much. Of course, costs can be a barrier for some people. Some of these altitude tents, we're talking in excess of £10,000 or dollars. So for someone that just wants to get their hands on hypoxic training, what would be a very entry-level piece of equipment that they can use that would still give them some benefit, but without emptying the wallets and without having to move somewhere to live for 6 weeks?
Yeah. I mean, cost is an issue for sure. And nothing. There's very, very few things that are effective which are not relatively costly, let's say.
Okay.
But certainly, when you think of the cost of an altitude camp, and the time involved as well, then I'd say probably the most cost-effective thing that we use with quite a lot of athletes are the altitude generators. They're portable. They're about the size of a large air conditioning unit, with a home mask. I use one of these. They're very reliable. I work with a company called Sporting Edge UK that supply them in the UK. They're about £3,000, that kind of price. So when you think of it, you think, wow, that's expensive. But actually, these are something that when you break that down to a per use cost, because you can use it all year round, it's not just like traditional altitude where you use it for like 4 weeks per year and that's it. You would use it kind of all year round. You might phase it in phases. You might share it with other friends, share the cost, use it with multiple people. It actually becomes relatively cost effective when we think about actually the impact that can have on your performance. How I often see altitude is that, particularly with kind of more training experienced athletes, so it's not necessarily an age thing, but people who have reached kind of the ceiling in what they can do with the time that they've got. So they've kind of come to a plateau. We talked before about hypoxia being a kind of a unique stimulus that presses these like adaptation buttons in the body that nothing else can. Well, that's where you can again remove that plateau. You can move it up to the next level with hypoxia. So if we're looking at something where everything else has kind of been done with all the supplements, different types of training, might be time limited to a certain number of hours per week. Well, here's an opportunity for something that actually will make a real difference if you do it correctly. Okay. So actually, the cost of that, when you spread it, particularly over a number of years, say, it's not crazy. It might seem a lot. If we think of other sports like, I'm involved a lot in example, use set of wheels, then you might have several sets.
Yeah, I was just going to say, I mean, that's just a set of carbon wheels, and
I think so. It depends all on the context you're working within and all the rest of it. So I'd say first and foremost, that would be a real thing you could do in that kind of price range. The next one would be, and this is what some people and even recreational athletes I know have invested in, that is the conversion of your home gym area. That might be a garden room, it might be or a bedroom, to an actual altitude chamber. Those conversions are not crazy expensive. I mean, they are a significant investment, but it's for some people that's not too much of an issue.
Yeah.
So again, there are companies that do that. The company I work for does that as well. So yeah, those are opportunities, and then really those are the, and obviously then there's the sleeping with tent business as well. And so just you said it's that kind of price point where you have a tent within a bedroom, which is not an airtight tent, but it's fairly air secure, and the generator feeds a reduced oxygen concentration into that tent, and basically you sleep in that several days a week, for sometimes 7, maybe 5, maybe alternate days, but you're spending 8+ hours in that, ideally a night or a day, to kind of get that simulated altitude effect of living at altitude and get those central adaptations. So those are the kind of...
Could you also use the mask? Sorry, could you also use the mask instead of the tent? So if you get the generator with the mask, could you use the mask when you're training, and also repurpose the mask for when you're sleeping?
Yeah, absolutely. They're effectively the same. They're the same generators. It's just the addition of a tent, or you use the mask at rest. You just need to accumulate quite a few hours. But in reality, you're doing the exercise piece, which is very, very, very potent stimulation for peripheral, but also central as well. Mm-hmm. Then you could top that up just with, in the evenings, watching television or
watching TV or
I haven't actually at the moment, but who will literally sit at their desk, they'll be typing away, so doing it in work hours, so you could accumulate hours each day as well. So I was
just going to say that if you work from home these days, where a lot of people do work from home, you could be sitting there with the mask on, so you don't have to have the discomfort of having it on when you're sleeping.
Yes, absolutely. Just remember to remove it for video calls. That's all. It's a bit weird.
For sure.
Dedicated. So those would be the main things around that. I mean, there are quite a few other things that are going on that people might search for. So this list of things would be things like isocapnic devices, breathing devices, respiratory training.
What do you think of all those?
Yeah, so I'll talk about those. I mean, the main evidence for these is actually around ventilatory function, so pulmonary function, so breathing mechanics, creating stronger respiratory muscles, improving the actual mechanics of breathing in deeply, breathing out well. And if that's a particular restriction for someone, because some people are often restricted in ventilatory mechanics and pulmonary strength, for example, then those can be really effective at improving breathing. So they're not necessarily actually doing anything around hypoxia itself. Improving your ability to actually deliver air and oxygen to the body. And that dysfunctional breathing is a very common thing in athletes, where particularly at higher intensities, or if it's particularly in running, where breathing might not be in synchrony with cadence, for example. They're very quite common. So, but that's not really related to it.
But that's respiratory muscle training, right? You're talking about the metabolic cause of the muscles expanding and contracting the lungs.
Yes,
as you are exercising.
Which is an important component, but it's nothing to do really with hypoxia. Correct. We have something called a breath hold training, so apnea training, breath hold. Now this is really come from free diving, where people are training themselves to hold the breath for a long period of time and still function. And there's quite a few physiological responses from that. Now, I've been involved with some research. One of my PhD students years ago who looked at this, looking at the swimming performance. So we have what we call passive apneas, where you're literally just seated, and you're doing breath holds for long periods, like near maximal breath holds.
Kind of like Wim Hof kind of stuff.
And then we have dynamic ones as well, where you might do exercise during it. So for swimming, this would be diving into a pool and swimming underwater for 1 length, 2 lengths, whatever. And improving that capability. Now, there is a real physiological response and adaptation from that. It's usually beneficial. Where is found benefit which again is just limited evidence for the actual performance benefit of it for sports performance. Free diving, obviously, unquestionable. You can't really get very far with free diving without that capability.
Yeah.
But the knock-on effects for
endurance
performance when you can breathe normally is less clear. And where those effects have been seen, it's usually in quite short events. So the translation across to endurance is not there necessarily. There have been some studies have shown an increase in EPO for a similar reason. In an acute case, you're getting this decrease in oxygen in the blood because your tissues are using it, and so you do get an EPO response. But again, it's quite short-lived. It's quite acute, and so many of the studies are not probably done long enough to see that benefit from it. So that again, it has a potential maybe to add into people to maintain some of those central benefits. So rather than stopping hypoxia, getting no EPO response, you might just have these little spikes in there potentially.
Yeah.
But there's been very little research around the application of that, if you like.
What about isocapnic training, where you are breathing in a stable amount of, is it carbon dioxide?
Yeah, so you see breathing normal air, and then the system lets some gas escape. You're effectively remaining kind of CO2 stable, if you like.
Like a rebreather bag.
I haven't really seen much research as yet to show the true performance benefits of that. It isn't an area I'm particularly familiar with, but I have spent a little time. It is an area I want to look at, because there are some new devices around which seem to offer some potential, because there is some potential interesting areas. And again, it's not clear. It might be more for shorter duration events and longer term. So, but it is an area to watch and keep an eye on.
Yeah, it's a very low barrier of entry because it's not expensive. I have the isocapnic.
That's there.
So, I mean, it's $100. It's not $5,000 like buying an altitude tent. So, it's worth trying for what it costs.
Yeah, exactly. And I think it's all these things. It's actually it's a good body of evidence that shows the physiological basis for it and the application, the outcomes. And it's trying to separate kind of fact from fiction and marketing hyperbole from reality as well. And there's some of these areas and tools where there's just not enough clear independent kind of research showing us what's happening from that. But it's not to say we won't get there, but right now it's difficult to say whether they have an impact or not.
Still early stages.
Yeah, and it might be again one of these tools where we get really potent stimulus from true altitude, and then we use these other ones to kind of maintain or top up, because that's always our challenge. Is that if people are using terrestrial altitude, well, there's always logistics and going from that place to home to competition and timing. You can't always take your altitude generators with you wherever you go and all this kind of stuff. So can we use a number of tools to just, they might not be ideal, but they're just enough to kind of keep that adaptation going before it dies away completely. So the one I would say has probably the most promise that people may have heard of is blood flow restricted training.
Oh yes, yeah.
So, and again, it's still relatively recent. There is an increasing amount of research, and it does look quite interesting. But the outcome effects of using blood flow restriction for endurance outcomes is a little bit mixed in terms of performance outcomes and truly affecting the physiology, which impacts on performance. But part of it is due to, again, the design of the research studies, the participants, the protocols that are being used, and also the blood flow restriction devices themselves. So the most affordable ones are effectively kind of Velcro bands, thick straps, and this is where you would put them around the top end of a limb,
muscles,
the muscle. So up, under your armpits, your arms, and up around top of your thigh. And you apply a certain kind of pressure, you strap them up to a certain tightness, and that will create a certain pressure. The problem with the straps, which are very affordable, I think literally less than $100 potentially, it's very difficult to kind of standardize that, how much flow is included, so the pressure. Because what you're trying to do is not stop, but reduce the blood flow to the muscles. So you would create a similar kind of local hypoxia, if you like.
Okay, yeah.
So because in that limb, if you reduce the blood flow, again, less oxygen is going in there, you're using oxygen, less is going in there. So some of it's to do with that variability in pressure, so how much flow is actually coming in and out. And where there is better control, you can get control with inflatable cuffs, a bit like blood pressure cuffs. Where you can set the pressure, so it's very repeatable, and you can be at a safe level, because you don't want it too tight either, because that can be quite dangerous or damaging. But they're quite expensive. Now you're looking at more like, I think, $2,000, that kind of price range. You see. So the research, depending which device they've used, depending on the intervention, is very mixed in terms of outcomes. But it is quite interesting. The most convincing research is for improvements in strength, actually, rather than endurance. But I think there's certainly something we'll find over time where we can find the right protocols, the right pressure to kind of again maintain some of these responses. It's only really good for those muscle groups where you can clamp, so arms and legs. Obviously, in running, for example, the glutes are a massive part of the running stride.
You can't really clamp the glutes, right?
Clamp those at all.
But for cycling with your quads, that might work a bit better.
Cycling, that's one of the modes that's researched quite regularly. So there is some limitations there as well. So I think that potentially, and it is an area to watch for sure, because I think that is probably the one out of all the others, other than pure hypoxia, which might have the biggest kind of hypoxic effect, combined effect. But there are other things that happen. We're also building up with, metabolites can't be extracted either because the blood flow is restricted. Localized carbon dioxide builds up in the muscle as well. So there are some other things that are going on which may not necessarily be important to us for endurance, let's say.
All right, fantastic. As we land the plane, Barney, within the realm of hypoxic training and breath training, if someone listening wanted to get the biggest physiological return for perhaps the lowest amount of money or the least additional time invested, what would you advise them to invest your time and money in?
Yeah, well, if it's related to hypoxia, I think for sure the most cost-effective route to effective outcomes is an altitude generator. It just gives so much flexibility for when you do it, how you do it, the exact altitude, the intervals that are specific for that individual, the way we can monitor it and get that kind of dose, hypoxic dose, and progressively increase it. I think that's the most successful route. Or
is there a brand that you recommend?
Well, yeah, I mean, I'm a little bit biased because I have an association with Sporting Edge UK. They're a UK brand, but I've got first-hand experience of the quality of their devices. They're very safe, they're well controlled, which isn't the same for some of the other ones, which I won't name, that I've used before, where actually the outputs aren't quite what they are.
And do you use that brand in your lab as well?
We use that brand in our lab. They've actually generated our they make environmental chambers, so we've had their environmental chambers for many years as well. They make room systems, everything. So they're a worldwide kind of leading brand in the area.
So you have a lot of experience with their products, and a lot of top-level athletes that you work with are using that in the UK.
But obviously that's a caveat. I have a association with them as well. So
that's fair enough. I mean,
brands are available, obviously.
Correct.
But I think that would be my approach. Would be using altitude generators. But obviously, if someone's got more time and more resource, going to altitude as well is also very convenient. Sometimes the locations are really nice places to be and train, because the training camp effect, change of scene, change of location, stunning scenery often. So, there's all that to bear in mind, but often it's a
Correct.
combination of different things that you need to do. But I think for recreational athletes, if you're serious about what you're doing, I think altitude, it should be certainly considered, and then you can, do your research, do your thinking behind it. So is that something you want to invest in, cognitively and logistically and in terms of time, because it can be very powerful, but it's not something you just can play with. You've got to do it right.
Okay. I won't call this a trick question, but a quick fire one. So you're a cyclist. If you were to invest some money of your own between the chamber or the machine that generates the lower oxygen and a pair of brand new top end carbon wheels, where would you spend your money?
Well, I have to caveat this a little bit with, I had a previous life of running a wind tunnel for cyclists. So I've done a lot of time looking at and measuring the aerodynamic properties of various wheels, rim widths, depths, yaw angle, speeds, all the rest of it.
Yeah.
And without a doubt, now with that kind of combined head-on, I would say, unless you want a pair of really old spoked wheels, I would suggest that the hypoxia, if you've not done it before, and you've kind of, certainly got the rest of your training in good order, so it's consistent, it's well suited, it's specific to your needs, then yeah, I'd say without doubt, hypoxia is probably something to seriously look at. Because
over the wheels.
Over the wheels, yeah, for sure.
Okay.
Yeah.
Okay. So you get a bigger bang for your buck.
Yeah, for sure.
Yeah.
Yeah.
Okay.
Because in reality, most people are, they've got a decent set of wheels already, and by spending, $2,000, $3,000, $4,000 on another set of very slightly better wheels, won't have
Margin of gains
of an impact. I mean, there is an impact for sure if you get it right for the right conditions, but hypoxia is pretty big.
Okay.
It's bigger, for sure.
Yeah, better improve the physiological side, aerodynamic.
In that scenario, yeah.
Okay. All right, Barney, my closing question for you is, what does endurance mean to you?
Nice one. Oh, it means so many things, doesn't it?
Yeah, it does.
I mean, I have so many hats for that because I'm an endurance athlete myself, although not practicing at a particularly high level these days as I get on. But I personally, I find endurance sport wonderful. It's rewarding. It's enriching. The feeling, the challenge, the results, the suffering. I love it.
Yeah, the suffering especially, right?
Yeah. And it takes you to some amazing places too. But yeah, from a physiological point of view, it's incredible. I find it fascinating because all the time you're striving for adaptations that help the body perform to a higher level. We're looking at kind of optimization of cells, of structures, of integrating mechanisms of cardiovascular supply and control and use in the muscles and everything around the support of that. So I find it just a lifelong fascinating puzzle and exploration of discovery as we learn more about the sport and how we can push ourselves individually at any athlete level to improve and perform at a higher level. Yeah. And the health effects that go with it. Amazing.
Barney, thank you so much for such a valuable conversation.
You're welcome. Been a pleasure to talk to you.